page as well.
All right, well, thank you so much. Let me see if I can share my screen. Always good as possible. Let's see if that, does that help? Can people see that? Yes?
Yeah,
Yes, we do.
Okay, great. Well, thank you so much for that very generous introduction. And I also, yes, on behalf of everyone, Bill, Erez, Yvonne, all of the organizing group, welcome to everyone to the second Inverse Generative Social Science Workshop. A huge bunch of activity I know you've brought. I'm thrilled to hear all of the work that's underway and to hear our great keynotes from Scott and Matt. So I've prepared a kind of overarching, maybe provocative, hopefully provocative talk on the goals really of the enterprise, you know, the workshop, but also the enterprise really of generative and inverse generative social science, and specifically on how artificial intelligence, machine learning, this cluster of techniques, how they can enable inverse methods that can allow us to improve agent-based modeling. I'm especially interested in the social sciences, but as Bill said, it applies to all sorts of topics. I've tried to focus on what I think of anyway as foundational issues, although there are a lot of technical ones and other topics that I love to get into. But I think, again, to reiterate what Bill was saying, the main idea is really to explore the possibility of, you know, we've all been working on the forward problem. That is, you know, we handcraft agents and see if we can grow the target. And instead of doing that, instead of handcrafting agents and growing a target, which is the forward problem, we'd like to start with the target and evolve the agents, even families of agents that generate the target. This is really the backward problem. And I think AI, machine learning can help us solve it. And that would be, I think, a very big move for our field. I think the idea raises several foundational issues, and I want to frame them, starting with a few words on sort of plain vanilla generative forward social science, at least as I think of it. I think there are several important distinctions, and at the risk of being slightly pedantic, I wanted to go through some of these and then talk about more of the kind of immediate AI type issues. But one of the important distinctions that I have in mind is really between explaining and predicting things. I think it's important that the social sciences, economics, other formal social sciences, adopt a generative explanatory standard. And I'll talk about what I mean by generative, but we certainly want to distinguish between explaining and predicting. And we'll come back to this because I think AI has been largely worried about predicting and not so much about explaining. But for example, you know, why are there earthquakes and tsunamis? We have an explanation. It's plate tectonics, but it doesn't let us predict when the next earthquakes and tsunamis will happen. Why are there new viruses? Explanation, evolution. But we can't predict the next flu strain, the next COVID variant, lightning. Electrostatics, can't predict where. So I think one point is in general, and of course philosophers can correct me on this, but I think explain does not imply predict. And conversely, here's this great data from the Hudson Bay colony of hair pelts. These are pelts they sold every year. Lynx data. And this is Lynx sales data for the Hudson Bay colony. I should have labeled the axes, but you see that it cycles around. And this is actual data. So you could say, can I predict what's going on in year T+1 from year T? Here's the data, can I predict? Sure, I can fit that data beautifully with a you know, autoregressive moving average model, a lagged equation. And it says, you know, I can give you the next year's pelts from the previous year's pelts. Clearly able to predict, fine. Does it explain? Does it give a mechanism for the cycles? And I would say, well, is there anything missing? Yeah, rabbits, the rabbits are missing. So you'd like to have a more, you know, the ecosystem picture is a deeper explanation of the cycles than simply a Fourier analysis of this time series, right? So we're interested in explaining, giving mechanisms, understanding why things happen, not just predicting them, not just describing them mathematically. And I think they're logically independent, right? You can explain without predicting, and you could predict without explaining. As I say, I think AI has largely been doing the latter, and we want to reorient it toward doing the former. That's the idea, I think, one idea of the workshop. But, I'm interested in a particular kind of explanation that, there are many names you could have chosen for this: effectively computable, constructivist, recursive. And there's a long history of generative process theory that Lars Erik Cederman has reviewed nicely in the IGSS. But the idea, at least to me, throughout has been to explain a pattern, segregation pattern, wealth distribution, history of a civilization, whatever it is. You have to show how the pattern could emerge on timescales of interest to humans in a population of cognitively plausible agents. And the agent-based model is the principal scientific instrument of this enterprise, I think. We'll come back to what cognitively plausible agents are. But we're interested in explaining, we're interested in generating as a form of explaining. And again, other distinctions that I think are important is this is a very different idea than equilibrium as an explanation. The Nash equilibrium picture is, if placed in the pattern, no agent will unilaterally depart from the pattern. That gives no account of how they attain the pattern or how long it might take them to get into the pattern. It might explain that if they're put in the pattern, it persists, but it doesn't explain how it was attained. And of course, if the pattern isn't in equilibrium in the first place, it's not a useful idea. Similarly, we're not interested in hyper-rational agents. This is the kind of Gary Becker optimal control picture. His famous paper with Murphy was called Theory of Rational Addiction. I think it would be more aptly titled An Irrational Addiction to Theory, but that's for another topic. But in any event, this sort of thinking is beyond humans. It's not cognitively plausible in my view. And I think that's been demonstrated pretty incontrovertibly. It's also not necessary. There's a lot of modeling that does nicely explaining phenomena without recourse to it. All right, so we're not talking about equilibrium. We're not talking about perfect rationality. These are the kind of agents we're trying to evolve, as Bill said. We're also interested in bottom-up explanations, as we all know. And this is distinct from another type of explanation or another usage would be as in macroeconomics, macroeconomic regression. Very indispensable, very important tool. And it might predict the response of an aggregate variable to changes in one or more other aggregate independent variables. But it's aggregate to aggregate, it's macro to macro. We want bottom up, micro to macro, this sort of thing. And to a generative social scientist, I think the aggregate relation, the regression equation itself is the explanation. That's what you're trying to explain. You're trying to grow this relationship that's represented in the regression equation. So, when I'm challenged often with the question, couldn't you just do that with a regression? I think the answer is really no, you couldn't do that. It's circular, in fact. You can't explain or generate the regression with the same relation. You want to explain the macro to macro relation by generating in some lower level micro specification, some agent-based model. Even though the macro relation could be predictive, that's what you're trying to explain, the relation itself, right? And of course, I'm saying micro to macro when clearly there are all these feedbacks from an interaction between levels. Agents, eat the sugar, that changes the landscape, that changes the agents. Agents in their environments change one another. And I don't think there's too much need for very convoluted language about upward and downward things. I mean, it's clear that, the agents change their environment, that feeds back to change the agents, and so it goes. So I don't think there's any need for very fancy language about that. But just to introduce some, I thought I've tried to be careful about this distinction also. Again, these are all things to keep in mind when we're growing agent models, agents as outputs, not inputs, that, the criterion is a criterion for candidacy, for explanatory candidacy. And we're trying to enlist AI in producing more candidates. Right? We handcraft some, but we'd like others. Anyway, the idea is, if you didn't generate it, then you didn't explain it. It's a negative criterion. It's a necessary condition. And the way I wrote that was, for any X you're trying to explain, if you didn't grow it, you didn't explain it. But that's very different than if you grew it, you explained it. Merely growing it isn't explanatory. I mean, there could be monkeys at typewriters that produce rules that generate the same, segregation patterns or history of the Anasazi or what have you, that are obviously silly and not explanatory. So I'm not saying if you just grow it any old way, you've explained something. But I am saying if you didn't grow it, then I don't think you've really got your teeth into it, right? So it's a necessary but not sufficient condition. It raises a question, this micro to macro thing. Sometimes there's a little confusion about this, and another distinction I think is, to keep in mind is posit versus generate. The motto is if you didn't grow it, you didn't explain it. That's not the same as a diktat that you have to grow everything in your model. Sometimes this arises, and some elements of every model have to be just posited. Those things can be very important actors. They can be agents in their own right. They can be intermediate institutions and so on. But it's just a definition. If it isn't generated, it isn't explained, that doesn't mean it's inessential or forbidden, just that it's posited, not generated. And I think in any model, some things have to be posited. Otherwise, you're in an infinite regress that demands that every generator itself be generated, and it's turtles all the way down, which is not useful. So not everything can be a theorem, right? There have to be axioms that are not themselves deduced from prior propositions. So I think we should resist that demand that everything be generated, which I get sometimes. And I think that's the same in all sciences. You're always looking for more fundamental unifying laws that mathematically entail the ones in hand, right? That's progress. Just as an aside, again, when I say IGSS, some people say, well, should we insist that physics do that? And I'm saying, no, I'm not insisting that physics adopt the grow it to show it standard. I'm interested in social science. That's why inverse generative social science. But I am insisting on cognitively plausible individuals, not the Becker, Richard Bellman, perfectly informed, infinitely empowered creatures. But so cognitively plausible individuals. Now, we can argue about what that means, but I think by any definition, atoms will fail the definition. So I don't think we're talking about physics here. Although it's worth noting that Newton was pretty unhappy to have no generative mechanism for action at a distance. And the whole gravity waves, gravitons, this whole move is an attempt to provide such a mechanism. So while I wouldn't insist that physics adopt our standard, I think physics is actually interested in it. Now, here's more directly related to AI. So those are sort of overarching issues that I think people should keep in mind, because I get a lot of confused reactions to what we're doing. And I think if we keep these distinctions in mind, we can preempt some of those. But now let's talk more about the direct role of AI in all of this. So the motto is, if you didn't grow it, you didn't explain it. Okay, fine, but there might be lots of ways to grow it. And we're not claiming that every generator is unique. There may be lots of ways to grow it, lots of agent specifications that are sufficient to generate the target, whatever that is. Chatika Gunaratne and Ivan Garibay have been doing wonderful work along these lines. I don't know whether Chatika is planning to show his inverse Schelling segregation modeling, but it's very, very nice. And the work he and Ivan did on inverse Anasazi model, it does better than the one Rob and I and others published. Those are wonderful examples. And I think that's why we're here, right? We're saying there's lots of ways to grow it. And we've had lots of success handcrafting agents, dreaming up agents that do nice things. But it would be nice to make that a little more systematic and to employ AI to produce larger families of these. And a lot of this is going on, as I say, evolutionary model discovery that I just mentioned, rule induction that Bill is doing, computational abduction, to hark back to Peirce's word, about which Pat Grimm and other philosophers would I'm sure inform us. Inductive game theory that's happening a little bit at Santa Fe. So a lot of us are getting at the same idea. We're trying to figure out, can we generate families of generators, inverse generate families of forward generators, right? And again, for social scientists, I think we're interested in illuminating human behavior. And I don't think that's really how AI has been used. I mean, AI is displacing humans at work. It's augmenting humans in all sorts of tasks. It's crushing humans at chess and Go, but it isn't explaining humans. It's beating them, but isn't explaining them. You could beat a human runner with a car, but the car doesn't illuminate how humans run. So I think we're interested in using AI in that way. Want to enlist it in this enterprise. And just as a fun example, I mean, when Gary Kasparov beat IBM's chess machine, Deep Blue, he did it with a brilliancy, a clean sacrifice that was very startling and allowed him to win. And after that match, he was interviewed and was asked, "How did you come up with that move?" And Kasparov's answer was, "It smelled right." And I think we're doing a lot of things by smell without the explicit calculation of costs and benefits that we see in the dominant picture of rational choice. I think, having studied a little bit, the human fear apparatus, for example, is not choice-like at all, not entirely conscious, much less rational, but it exhibits regularities that we can represent in models, that we can replicate in experiments, and then we can introduce into agents, okay? So I think this is also kind of an inverse, not an inverse, but a different use of artificial intelligence that I think that we're interested in exploring. It raises another important distinction. This, I think, is really a rife confusion that needs to be addressed. When I say we're trying to illuminate human behavior, the AI is beating humans, but other things are doing other things, right? So there's illuminate, and there's emulate, and there's illuminate. And in this respect, I think the Turing test that we hear about often is completely irrelevant to our enterprise. Suppose I claim to have a cognitively plausible micromechanism that generates some target pattern, segregate something, right? And we're sometimes told, I'm sometimes told anyway, that, well, that's already been done because John Smith already proved that for any pattern, any target, there's a Markov transition matrix T whose absorbing state is also that thing. So what? How does the transition matrix illuminate the generating mechanism? So, for example, I could have here's the Turing test. Behind the screen is a human soprano and a perfect recording of the soprano. No human can tell them apart. But the recording tells me nothing about how humans vocalize. By what mechanism do humans generate sounds? It's wind flow across vocal cords. And the Turing test is just irrelevant to generative mechanism. It's like saying, I want to understand how the steam engine works, so I'm going to start by sampling clouds of steam. I'm going to collect enormous big steam data. I can find some model that generates the same steam data, but it won't illuminate how the steam engine works. I might even be able to predict steam on Tuesday from steam on Monday, but it doesn't teach me anything about the steam engine, how it works. So emulation of output does not illuminate mechanism. And I think this has been an issue, a confusion. And again, largely it's been about emulate output, not illuminate mechanism. And we want to reorient AI to this latter objective. Okay, now, when I say cognitively plausible agents, this is a big topic. There are new agents, next generation agents, what I might call ortho-rational agents, that include some emotions like fear, but others. They include social network effects, and they include well-documented errors in our appraisals of information and risk, bounded rationality. And I think these are going to give us deeper explanations of collective dynamics across a huge array of fields. But thus far, even those, and my own stuff is no exception, they're particular handcrafted solutions to the forward problem. And we'd like to use AI to evolve larger families of generators. Again, beginning not with the agents, but with the targets. And cognitively plausible agents, even families of them, then become outputs of AI-enabled inverse generative social science. And I think that will stand agent-based modeling on its head and allow us to address a variety of criticisms. One of these is, okay, you found a generator, aren't there others? We'd like to say yes, all the following architectures generate the target. And that would confer a kind of robustness, at least over a collection of generators. And it would be less ad hoc as often charged, but I wanted the charge of ad hocness, I think, can be met partially anyhow by saying, look, some agents are not entirely ad hoc, but they're rooted in relatively sound experimental psychology, even neuroscience and behavioral economics, whose novelty appears to consist in actually observing humans. I'm always surprised at how radical behavioral economics seemed. It was really like, you have 300 years of astronomy, and then someone has the temerity to suggest that you actually observe the planets. So nonetheless, it's been quite a productive move. And I think the real gripe about agent-based modeling is not that it's ad hoc, although that's one of them. It's that it's not unified in general, like utility maximization. But here, utility maximization really isn't unified if you can choose from a huge menagerie of utility functions. And now there are a great variety of these, including random utilities, prospect theoretic ones, constant relative risk aversion and its relatives, non-aggregable classics like Cobb-Douglas, Gorman utilities, logarithmic ones, and utilities based on lexicographic preferences, all discounted exponentially, hyperbolically, in every which way. So I don't think it's as unified as it looks when people say, well, utility maximization, rational choice, these are all, it's a nice, clean, very tidy area. It's getting less and less tidy by the day, I would say. Anyway, yes, agreed. IGSS will produce collections of generators, not just handcrafted agents. And if you have this cloud, this set of generators, that set is really the pre-image of the target under iteration, right? You iterate the model forward, you try to generate the target. So the pre-image of the target is that set of generators. Can we say anything about that set? What's the nature of that set? Can you metrize it, right? You often hear, okay, you dreamed up those rules and they seem to work, but what if we change the rules a little? Is the result robust? Change the rules a little. You'd like to be able to answer, yeah, the result is robust over an entire neighborhood of agents, over a neighborhood of rules, not just parameters, but rules. But what would that phrase mean? What could we mean by that? Neighborhood of rules, neighborhood of agents, right? Can we put a metric structure, a distance measure, on the set of micro generators so that you could say the fit is not just stable to parameters, but stable to changes in rules, in form, right? Could you say there's a neighborhood of agent models within which all of them generate the target so that it's stable to some type of variation in the structure of agents? So you're really looking for an analog of structural stability for agent-based models. We'd like that. I'd like that. What is this idea? Again, I'm not going to traipse too far into this, but it's a very important idea in dynamical systems in math, and a very beautiful one because it connects a metric property, a distance property, to a topological property, which is just about deformation, what's preserved under deformation. It has nothing to do with distance. So it's very beautiful connection. But the idea is, could you define a structure, but in math, it's define a structure over vector fields, functions, and say that within an entire neighborhood of fields, all the phase portraits, the flows, are equivalent. They're topologically equivalent. They're continuous rubber deformations of one another. They have the same equilibrium and stability structure. Could you do that for agent-based modeling? Could you say, yeah, we get the same qualitative results under any small change in the functional form of the agents? The flow is the same. So again, I understand what I mean by a small change in numerical parameters, or a small change or a neighborhood of a metrized function space. But what would we mean by a small change in rules in the agent model itself? I think that's important. If you want to say, it's how robust is it? It's robust to a small change in agent structure. What should we mean by that? Can we make sense of that? Do we have an answer? And I think we have too many answers, right? There's a million ways to metrize that space. Every program, and so every agent model, could be represented as a finite string of zeros and ones. So obviously the distance between two programs, since they're binary strings, could be the Hamming distance between them. And this has been used to discover CAs, cellular automata, with some interesting properties. And it's a perfectly kosher metric, but it may not be very illuminating. Again, it may not accord at all with our sense of proximity or similarity. So I say I could encode, all of these rules as strings, and I could say I could calculate the Hamming distance from the rule call mom to the rule write a poem. And I could calculate the Hamming distance from call mom to eat a potato. Okay, which is closer to call mom? Write a poem or eat a potato? What does it mean to say I changed the rule a little and the results stood up? I think that's actually an important problem for us. Now, of course, it's completely circular to say that the rules are close if the outputs are close. That's circular. Then we can't even coherently assert sensitive dependence, right? We can't even say that a small change in rules produces a large change in outputs. So that's obviously self-defeating. That's not a good read. We may end up not worrying about it, but I think we should ask how rigorous we can be about that. There are lots of possibilities beyond that. You can metrize a set without being able to order it. That's true of the Euclidean R2 and above. So you could give the distance from the vector 2, 7 to the vector 23, 0, but I can't say one is bigger than the other. So you might say I can't order them, but maybe I can. I'm sorry, this was about I can't metrize it. Or there are too many ways to metrize it. This is, I might be able to metrize it, but can't order it, right? Because I could metrize the space of two vectors, but I can't say one is bigger than the other. I could also order it without metrizing it by alphabetizing it. And I could do both, as we can with the real line. And you could do neither. You could simply encode it, the set of generators, as a searchable set. And that would allow one to come up with a lot of alternative microgenerators, but you wouldn't be allowed to say that there's small variations on one another, since the phrase really has no technical meaning. So I know that's possible, and I think it's a fine and fundamental step. And I think an excellent example from my own immediate set of colleagues is Chataka's inverse Schelling work that produces a family of 3- and 4-term utility functions, all of which have comparable generative power, but I don't know that you could say they're close to one another, or that they form a neighborhood in some metric space, or that they could be ordered. So again, just as a foundational matter, I think we should be thinking about these things, just to be rigorous. Okay, and on this whole issue, right, it would be every program could be written as a Turing machine or as recursive functions, which addresses another critique that you often hear, that agents, there's no equations for agent-based models. Sure there are. For any model, there's a Turing machine, and for every Turing machine, there's a recursive function. So there's a recursive function for every agent. So if we could invert Turing machines, we could certainly invert ABMs. But that's actually not been done. I've found very little on that. And the same for inverse recursive functions. So, if we were looking for a quick out from computer science, I don't think that exists yet. But correct me if I'm wrong. I've been able to find very little about that. All right. When I give this sort of talk, some people say, oh my God, it's the end of humans. It's the end of theory. The robot agent designers are going to take over from us all. And, I don't think that's really true. But I think the locus of theory might change from the completed agents to agent constituents, rules, modules, building blocks. The building blocks still have to be germane to the problem, right? It's not, pick a preferable Schelling site and also eat a cookie. That'll generate the same segregation pattern. But it's, it's superfluous, right? So there may be issues of parsimony and relevance that are also up to humans to decide. And we have to meet, again, defensible notions of cognitive plausibility. And all of that requires human judgment, but I think maybe at a different level, at the level of what are the primitives, what are the permissible concatenations, what are the modules. And I think much of this work has to start with a human model, as it does in the Schelling case and some of the other work we have underway. Another issue is, again, we might get a lot of generators and rule some out on these grounds of plausibility, parsimony, and so on. But it might be that the machine can't find any alternatives to the handcrafted agent, and you just plain nailed it, and that would be wonderful. There may be many, all equally good. Then there's more work, as in any science, right? If you have competing theories, generators, then you try to do more experiments and decide which is better. You introduce new data. I don't think we're in any more. It's just like any other science. I have two generators. Which is better? Well, maybe I can distinguish with new experiments or something. All right, and there may be no good ones. Right? There may be no good generators. The machine can't come up with any. I can't come up with any. That's where I am in several of my projects right now. But when you say you've got a good one, good also is worth worrying about. I mean, do you mean merely accurate, merely generate the fit, or do you also mean comprehensible? Here, I think AI is also, there are issues that arise in this field, and you might think about comprehensibility constraints, right? You want the generators to produce the target, you want them to be cognitively plausible, and all of these nice things. You also want them to be understandable, and I think there certainly are trade-offs between deep, highly accurate trees, expressions, agents that offer no theoretical insight, and less accurate but more understandable solutions. I mean, you might want a less accurate but more comprehensible solution. And just as an example from work I've been doing with Robin Pershouse, who's the PI of an alcohol NIH project, who will speak at the conference. Hi, Robin. We replicate alcohol use data using inverse generative social science, and have a paper along these lines. And here we're trying to replicate alcohol use data over a long time series of data. And the agents have 4 primitives. They have, what do they consider to be the payoff of drinking, their autonomy, all of these are defined carefully. Payoff, autonomy, and 2 norms, an injunctive norm, meaning something about what should people do, and a descriptive norm, meaning what is your appraisal of the frequency of the behavior. So there's payoff, autonomy, injunctive norm, descriptive norm, and 4 permissible concatenations, plus, minus, product, and square root. So there's only 4 nodes in these trees and 4 ways to assemble nodes into structures. And genetic programming produces lots of them with their calibrated, with their error and the size of the model, that is to say, the complexity of the agent. And some of them, what's inside the agent is a rule like this one, payoff times autonomy plus the square root of 1 minus 1 minus the square root of the descriptive norm. For those of you who, John Koza's work is full of expressions like this, although they're written in Lisp. But this is a kind of hazard of evolutionary programming. It produces these very elaborate trees that are very hard, that are highly accurate, but hard to understand. And in that work, we actually looked at this trade-off a little bit between comprehensibility and accuracy. And we can have very high accurate models, the 16 node rule, the 16 node rule, and this one, which is accurate but very hard to decipher, and this one that is easy to decipher but has a larger error. So again, I think this entire field of inverse generative social science, evolutionary programming, model discovery, and so on faces this kind of trade-off. It's another thing we should be thinking about as we break this ground. And in addition to being opaque, if you don't constrain the machine in any way, you can generate trees with more nodes than data points, right? It builds a kind of Borges map of the problem, which is also bad. So, there are all these questions to consider as we take this farther. There are calibration challenges that I think, might be unique to this area. Also worth discussion, lots to discuss. But, to summarize, I would say that, we have forward generative social science where we make these distinctions between explain and predict. We're interested in a particular kind of explanation that I've been calling generative. I don't really, there are other things you could call it. It's different from equilibrium, from optimization. It's different from regression. It isn't physics. We're saying growing is necessary, not sufficient. We want the generators to be cognitively plausible. I think it's important to have formal alternatives to the rational actor. I mean, I think one of the reasons, there's been a lot of criticism, right, from Simon and Kahneman, behavioral economists, and a huge number of counterexamples and the rest. But, to really change the field, you have to have formal alternatives to the rational actor. I think Samuelson said, you can only beat a model with another model. So we're looking for AI to produce formal objects, right? They're explanatory candidates, right? They may not be unique. There may be lots of ways to grow it. The backward problem is, can we make the search for those more thorough? Can we use AI, evolutionary programming, machine learning to construct, to discover families of generators, satisfying the explanatory standard with all of its desiderata? And then we can maybe face these questions of, robustness and stability and neighborhoods and comprehensibility and all of that. That's all out there that I think are very fundamental questions to make this enterprise more coherent. But IGSS connects that explanatory standard to those social science desiderata. And I think the unified field of forward and backward generative social science retains the standard, but revolutionizes the construction kit. So I don't think it's the end of theory. I think quite the contrary, it could be its rejuvenation. Mainly, I think there's lots to discuss. I thank you all for coming. I look forward to a great and formative conversation. Bill, I don't know what we're doing on time. I don't know whether we want to have a discussion or I should go directly into introducing Scott, or people would like to take a break, or I'm open to anything.
Yeah, I think we have a few minutes for questions. I did have a request, Josh, and all speakers for today, which is that, or for the whole workshop, if you could send me your slides.
Yeah, of course.
That they get up onto the website as well as the recording. And if you can send them to me ahead of time, that's even better, right? So that people can take notes on them. So I did want to make that quick announcement, and I'll reiterate that throughout today. But yeah, I think we probably, so it looks like Scott is here, but we do have about 10 minutes before officially we're supposed to kick off his keynote. So I think we probably have time for one or two questions if there's anyone from the audience who wants to ask a question of Josh.
Yeah, please. Criticisms, questions, everything.
I can throw something.
Yeah, Dante, I see your hand up there. Do you want to go ahead and unmute yourself and ask?
Yes, thank you so much for this. This is great. Professor Epstein, I always love your talks. My question here is, as you're thinking about the type of model that's going to be generated out of this, I think you're focused on the level of the rational or irrational or whatever it may be, but sort of like human in a sense, right? Like the zero agent. Could we think of more levels and in that way sort of like address the lack of consilience that we may have between disciplines, right? Like so one family of models could be like focusing on not the atoms, but potentially the psychology of the agents, as in the model that you presented working on alcohol use. And in another level is more like a sociological level of, like the end of history or something big. And then more of the level in which you and I may think more often of more like the economics of individuals generating this. But could we use this type of science to then say, hey, here's something that generates it at the sociological level, and here's something that generates it at the humans level, and then try to see if those models can be paired together. And I think this would be very useful for the type of stuff that I think Scott Page talks about in many models world, and see like, here's generative science that generates both of those models, and it actually makes them make sense of each other in a together kind of way.
I think I understand what you're saying, and I think I agree, and I think that's a good goal. I mean, I think there are all these intermediate levels. All these models have many different levels. And, you know, sometimes you posit intermediate levels, and sometimes you might try to grow them. But I think the mature models, I mean, if you can generate the model, generate the target, whatever level it is, intermediate or macro or meso level or something else, and also have an account of how that feeds back to shape agents, then I think it's a much more complete view of how society, how individuals and social phenomena, individual and social phenomena are related and co-involved. So yeah, I think that's a good objective. If that answers the question.
From Tim, it looks like.
Yeah. Hey.
Hey.
Yeah, this is great. I've been thinking about this whole what do you do with the simple way of thinking about the inverse generation problem is that it's a search problem, and you quickly realize that it's a search problem over an infinite space. If you don't bound it somehow, and you've done a good job of illustrating this, that the rules can become trivially convoluted, and you know you can actually come up with, well, how many agents should you have? What should their behaviors be? What should they be looking at? How should they be interacting? What should their parameters be? But it actually becomes infinite, and you can't search an infinite space. So the question then becomes, how do you bound that space so that you can search it? And then, of course, as you point out, in order to talk about bounding the space, you have to define the space so there's even anything to carve pieces out of.
Yeah, right.
But I think I just want to endorse that idea that really coming up with a way to define the space is really fundamental. And I think a lot of the meat of this question is probably about bounding it. How do you find the right boundaries so that when you search it for good solutions, you actually get things that are explanatory and maybe predictive and that actually do what you want them to do. But I think the way you find the right kind of stuff is not by searching better, it's by bounding the space better. And that's kind of where my head's, I think, going to be for the next 3 days as I watch what people are doing, is trying to figure out how to ask that question better at the end than it is now.
I agree completely. I think that's very well put. Couldn't agree more. I mean, I think we're interested in what I call the minimal generators. You want the simplest, most transparent model. So yes, it's all about bounding the search. I agree with you completely, Tim, and I think that's a fundamental problem in all of it. But yeah, I think that's crucial because we want agent models to still be elegant, parsimonious, transparent, recognizable, all of that. And I agree with you. That's not about brute search or evolution. It's really about how do you bound the space? So I agree. I think that's a very foundational concern. Thank you.
Thank you.
And then I see that Leo has their hand up, so they have a question.
Yeah, thank you for taking my question, and I really enjoyed your talk. My question is about, at one point you made an aside, a note about how you think that this model doesn't fit so well for non-social sciences like physics. And so my question is whether or not you're making that claim kind of to say, hey, inverse generative social sciences may be a separate project from and doesn't require that this method has successes in the natural sciences, which you're talking less about, or whether you think there are really methodological problems that prevent this framework from being extended to physics.
I think that's a great question.
That's all. Thank you.
Yeah, no, that's a great question. In general, I would say no. You could adopt the same notion of explanation in physics. And I think physics, in some respects, is moving in that direction. I mean, as you descend into more, from gross macroscopic laws like Newton's laws to the level of quantum theory and so forth, you are, in fact, generating the observable behavior from lower and lower levels, right? And from more individuated, particulate accounts of the universe. So no, I think in principle, you're right. I think I would stand behind the extension of this definition of explain, certainly to the natural sciences, but I'm also possibly to physics. I mean, I think it's a deep question, but I think in general, I might be inclined to agree.
Great, Josh. It looks like we have time for one more question. I see that John Greffenstedt has had his hand up for a while, so why don't we go with this question?
Hey, John.
Hey, Josh.
Hey.
Good to see you.
Likewise.
Hey, I'm thinking about what the boundary between starting with a specific model and generalizing it, and when that becomes a generative approach. So you can start with a specific agent model. You can replace constants with parameters. You can maybe continue to do that. And so when you first do that, it just becomes maybe an optimization issue. But then you could also think of ways of, mutating rules, adding terms, and so on, sort of from a bottom-up approach from a single example. Where does the boundary happen where you say, okay, now we're now exploring an interesting set of spaces?
I mean, I'm not sure there's a clean answer to that. I certainly agree that and I tried to say this, but very briefly, that I think a lot of these exercises could begin with a human model, a well-known human model, and then mutate it, vary it at the level of rules and concatenations and other things, and see what sort of bloom of models you get out of that. I think that's fine. Although I have to say, Robin and I, we started that alcohol model with a human model that isn't even on that curve. When it's so bad that that it doesn't even get into the list of generators discovered by the machine. So I think that's a fruitful approach. We're certainly doing that, but I think it may turn out that that it's possible to do it without any origin, any agent origin. But I think certainly, and all,
You can
let 100 flowers bloom. Yeah,
you could also start with a set of human generated models.
Absolutely.
Yeah.
No doubt. All very sensible. Yeah.
Josh, with that, I think we're ready to introduce.
Okay, great.
Scott, so you're going to take that away, right?
Wonderful. Yes, absolutely. Well, thank you all for the great comments, and I look forward. If we were all together, it would be nice to be able to all have lunch and hang out and talk further and go out and carouse and so forth. But I look forward to that. Meanwhile, yes, it's my pleasure to introduce our first keynote speaker, Scott Page. Scott is the John C.